So in the last class, we did this problem. So if A is 0, 1, 1, 1, 0, 1, 1, 1, 0, and B is given by this matrix, show that AB into A inverse is a diagonal matrix. So first we found A inverse. A inverse is adjoint A by determinant of A. So first we found the matrices, the matrix, its minus, and then its cofactors, and then determinant is um, the matrix, the elements of the matrix along a row multiplied by its cofactors. So that's what we did here, and we got the determinant to be 1. Sorry, 2. And then we found the adjoint matrix. Adjoint matrix is the transpose of the cofactor matrix, and adjoint A by determinant of A. So we got this. Now what we have to show, A into B into A inverse. So let's do that. So first we'll find A into B. A is this is A, and B is half of B plus C, C plus A plus B, C minus A, B minus A, C minus B, B minus C, A minus B, and A minus C. Okay, now this is half of, now let's multiply 0 times B plus C, then 1 times C minus B, plus 1 times B minus C. So it is 0 times the first element here, then addition of these two. So C minus B plus B minus C will give you 0. Then next, 0, 1, 1 multiplied by the second column. This is 0. And then C plus A plus A minus C. That will give us 2A. Next, 0, 1, 1 multiplied by B minus A minus B, and A plus B. Okay, this multiplied by 0 gives 0. 1, plus 1. So A minus B plus A minus A plus B, that will give you 2A. Now let us look at the next one. 0, 1, 0, 1 multiplied by the first column. So B plus C plus B minus C, we will get 2B. Then this multiplied by the second column. C minus A plus 0 plus A minus C, you get 0. The last one, you add 1, 0, 1. So B minus A, 0, A plus B. So A cancels, you get 2B. So similarly, you can guess the last one. Last row multiplied by the first column, you get 2C. Then multiplied by the second column, we again get 2C. Multiplied by the third column, we get 0. Now, we have A, B into A inverse. So half of this, we can of course take 2 common. because it's a matrix. 2 will come throughout the entire matrix, all the rows, all the columns. It's not a determinant that, and determinant, 2 will come out of only one row or one column. And A inverse is half of -1, -1, -1, 1, 1, 1, 1, 1, 1. So this is half of. Now you look at this. 0 AA multiplied by -1, 1, 1. So you get 2A. Then 0 AA multiplied by 1 -1, 1. So you get 0 minus A, 0. Next, 0 A multiplied with 1, 1 minus 1. So 0 A minus A, 0. Next, B 0 B multiplied by the first column. You get minus B 0 B 0 multiplied by the second column, B 0 B 2B. Then B 0 B multiplied by 1 1 minus 1. So B 0 minus B 0. Then minus C plus C 0. Minus C 0. C 0 to C. Okay. This has a term in matrix operations. This is called as diagonalization of a matrix. It is valid for certain type of matrices. It's not that all the matrix will give you a diagonal matrix. So this we got as a diagonal matrix. That is what we had to show. This is a diagonal matrix. So our portion for the intermediate exam is over. All right, with this. However, there's a very important chapter. I don't know whether they will include it for entrance exams or no. It is too early to say. But there is a very important application of matrices. That is in solutions to linear equations. So I will cover it. In 2 classes, I'll cover it. Before I introduce the concept of rank, I will introduce this one, the Crammers Rule. Okay, solution of linear equations by determinants. Okay, I'll explain this. The Crammers rule for single and for equations in two variables and equations in three variables. Okay. Now, how do you find the solutions to equations? Now, let us go by the simple first one, solution of system of linear equations in two unknowns. Okay, what is a linear equation in the first place? Linear equation is um, equation in which all the unknown variables are of single degree. So now, system of linear equations. First case is two unknowns. It is two unknowns. System of linear equations and two unknowns. So you have here a1x plus b1y equal to c1, a2x plus b2y equal to c2. Okay. So how do we solve this? Let us go by the general methods of solving. Solving the two. Solution to the equation to the above equations is the ordered pair x comma y, all right, which satisfies both the equations. All right. So when you say solution to a system of linear equations, this is of two unknowns. So you will have two equations. Then a value of a pair x comma y which satisfies this particular equation, both the equations, is called as the solution to the system of equations. All right. Now each one has a geometrical side to it. We won't go at this level, but I'll just introduce the concept of Cramer's rule for you. So suppose now when we are solving, eliminate y. Let us see what happens. Okay. To eliminate y, what do we have to do? Multiply the first equation by coefficient of y of the second equation and multiply the second equation by the coefficient of y in the first equation. So when you multiply, you will get b1, b2, y, b1, b2, y. Now subtract this. What happens? This will eliminate y. Here we get a1, b2 minus A2 B1 times X plus 0 is equal to B2 C1 minus B1 C2. Okay. So what is X? B2 C1 minus B1 C2 by A1 B2 minus A2 B1. This we can write as determinant. You see this C1 C1 C2 B1 B2, correct? And this in the denominator we can write this as A1 A1 B1 A2 B2, isn't it? Determinant of this is C1 B2 minus C2 B1. That is what it is. The bottom one determinant is A1 B2 minus A2 B1. So this is X. Similarly, eliminating Y. Sorry, eliminating X. We have eliminated X. Eliminated Y in the first case. Now eliminating X. So A1X plus B1Y equal to C1. A2X plus B2Y is equal to C2. So what do we do to eliminate X?
Multiply the first equation by A2 and second equation by A.
Good. And subtract. So you get 0 plus A2 B1 minus A1 B2 times Y is equal to A2 C1 minus A1 C2. To have a commonality with the above equation A1 B2 minus A2 B1, I will multiply with a minus sign throughout. So I'll get this as A1 B2 minus A2 B1 times Y is equal to A1 C2 minus A2 C1. This implies Y is equal to A1 C2 minus A2 C1 by A1 B2 minus A2 B1, which is equal to A1 C1 A2 C2 divided by A1 B1 A2 B2. Okay, you observe the pattern now. Okay, I'll write here and then so X is determinant of C1 B1 by sorry, not by C1 B1 C2 B2 by.
Sir, could you say why did we write that y equals to A1 C2 minus A2 C1 by A1 B2 minus A2 B1 as A1 A2 C1 C2 by determinant A1 B1 A2 B2, sir?
This one.
Yes, sir.
The numerator is the determinant, na? A1 C2 minus A2 C1.
Yeah, okay,
Denominator.
sir. Yeah, got it, sir. Got it, sir.
Uh, okay, now you see. Now look at the simultaneous equations. I'm writing here a1x plus b1y equal to c1, a2x plus b2y equal to c2. Here in this equations, uh, you should remember that the constant is on the right side of the equation. Constant is not on the same side of the equation. The c1, c2. Just you have to just note this. Now I will call delta. This is the Crammers delta as the coefficients of x and y. Take the coefficients of x and y and take the determinant. A1, B1, A2, B2. All right. I will call delta x. Sometimes people call it as delta 1, but because I am trying to solve for x, this particular determinant here, I get that determinant by replacing the coefficients of x by constants. So in the original determinants of the coefficients of x and y, if I want delta x, I replace the coefficients of x by the constants. Okay, keeping the other elements as it is. All right, then we define. So next, delta y. We define delta y as take delta, replace the coefficients of y by constants. Got it? You see here now. So by Crammers rule, solution to the equation exists if delta is not equal to 0. All right. If delta is not equal to 0, solution will exist. And at least one of no 0, sorry, this is not applicable for this condition. Solution to equation exists if delta is not equal to 0, and solution is, and the solution is x is delta x upon delta, y is delta y upon delta. See here from the previous step. Okay. So by determinants, we are finding this is the solution. Now, so if delta is not equal to 0, when will determinant be equal to 0? When the coefficients of the elements of the row are proportional. If elements of the row are proportional, going back to the concept of straight lines, these two represent straight lines. If coefficients of x and y are proportional, it represents parallel lines, right? It represents parallel lines. So when delta is not equal to 0, it represents lines which are not parallel, and lines which are not parallel will intersect at a single point. You get a unique solution. All right, this is a case of a unique solution. Okay, we call such a system which a unique solution as the system is consistent. Consistent means it has solutions, and determinate. Determinate because you have a unique solution. All right. The system is consistent and determinate. I'll explain all this in this is a very consistent means it has solution. Determinant means it has unique solution. All right. Next, now if you just observe this, delta is equal to 0 and delta x and delta y are also equal to 0, then basically we derived this expression from delta into x is equal to delta x. That is what we got here, isn't it? This is here. This is delta and this is delta x. All right. Delta into x equal to delta x. All right. So you just look at this. You get delta into x as delta x and delta into y as delta subscript y. Now, when this is 0, 0 into x equal to 0 and 0 into y equal to 0, then, okay, then what happens? The system will have infinite solutions. There are infinitely many solutions because x and y can take any values. Are you understanding? You may wonder why for a small problem like this we are doing. However, its importance will be known only when we do huge, big size problem, even 10 by 10. So 10 unknowns, 10 variables. If you don't have to solve the equations first, you just have to find the determinants. And based on this, you can identify whether it has uh, infinite unique solution or infinitely many solutions. So the system is said to be, the system of linear equation is said to be consistent and indeterminate. All right. Why indeterminate? Because you get infinitely many solutions. From point of view of straight lines, these two represent straight lines, right? These are straight lines. Now you observe this. Delta is 0, delta x is 0, delta y is 0 means a, b, a, all the coefficients are proportional. a1x plus b1y equal to c1 and a2x plus b2y equal to c2. Both the coefficients of both the equations are proportional, which means they represent, can anybody tell me what? What do they represent? If two equations, two linear equations have proportional coefficients, what do they represent? a1 by b1 equal to a2 by b2 equal to a2 by c, a1 by a2 is equal to b1 by b2 is equal to c1 by c2.
Coincident lines.
Very good, very good. So this represents coincident lines. The lines are coincident. That means there are infinitely many points that satisfy both the equations. They are coincident lines. So therefore you get infinitely many solutions. Understand? This is unique solution. Here you get infinitely many solutions. Or we say infinite solution. Because every point on one line will satisfy the equation of the other. Third, if delta equal to 0 and at least one of delta x comma delta y is not equal to 0, then what happens? Delta is 0 but delta x is not 0. You just think about that situation. Okay, this is 0. 0 into x is a non-zero value. Will it be possible? Is it possible?
No, sir.
Hmm. So this is not possible. There is no value of x and y that will satisfy this equation. Therefore, the system has no solution. We say the system is inconsistent. Inconsistent system. So did you understand the three cases? One is unique solution, other is infinite solutions, third case is no solutions. Okay. Hmm. So here conditions for consistency. It is said the following cases may arise. If D, here I wrote as delta in the here I wrote as delta. There in the here it is written as d1. This is same as I'm writing here. This is same as delta. This is delta x. This is delta y. Okay. So when d not equal to 0 means delta not equal to 0. Then the system is consistent and has a unique solution, which is given by Crammers rule. X is, oh, this is for third one, any guess? X is delta x by delta, y is delta y by delta. We'll come to Z now, three unknowns. And if d is equal to 0 and at least one of the other determinants is non-zero, the given system is inconsistent, it has no solution. And if d is equal to 0 and all the other determinants are also 0, the system is consistent and dependent, it has infinitely many solutions. Okay, this is the Crammers. This particularly the first result is called as the Crammers solution. Now this is for 2. This is for a system having 2 unknowns. Now for 3 unknowns, so we have the simultaneous equations as ax a1x plus b1y plus c1z equal to d1, a2x plus b2y plus c2z is equal to d2, a3x plus b3y plus c3z is equal to d3. This represents plane, equations of a plane. All right. The previous case represented equation of a line in a 2D geometry. This represents equation of a plane in 3D geometry. This is there in your intermediate. However, they have removed planes for this particular year. They have reduced the syllabus, but this is a very, very important component. Um, in any case, now we define delta. We define delta. We define all of these like this. Sorry. We define delta as determinants of the coefficients a1, b1, c1, coefficients of x, y, and z. a2, b2, c2, a3, b3, c3. Then delta x. Delta x is, how will you get delta x? Now you tell me, based on the previous result for um, two variables case. Delta x.
A1, A1 C1, A2
No,
C2.
no. We
Start.
replace the coefficients of x by the constants. In delta, replace the coefficients of x by the constant and keep the other two as it is. Okay. Then how will you get delta y?
Sir, shouldn't it be A1, A2, A3
Which one?
for delta x?
No, delta x, you have to replace coefficients of x with the constant. See here, we replace coefficients of x by the constant. For y, we replace coefficients of y by the constants.
Okay, sir, sorry.
Got it? So delta y in the delta determinant, Replace coefficients of by constant. So you get A1, A2, A3, D1, D2, D3, C1, C2, C3. Okay. And what is delta Z? Replace the coefficients of C1 of Z by constants. First, delta will have coefficients of x, y, z. Delta x will have constant coefficients of y, z. Delta y will have a coefficient of x, constant, and coefficients of z. Delta z will have coefficients of x, coefficients of y, and constant. Okay. Now again, by Cramer's rule, the same three conditions apply. Okay, the three cases. So case 1, if delta is not equal to 0, then solution exists. All right, and x is given by delta x by delta, y is given by delta y upon delta, z is given by delta z upon delta. Again, there is a unique solution. What do we call this system as? What do we call this system as? The system is said to be, again,
Consistent
very good,
and
determinate. System is said to be consistent and determinate. Second case, now you tell me, if delta is equal to 0 and delta x, delta y, and delta z all are zeros, then what do you get? Infinitely many solutions exist. All right. The system is, what is it? What do we call? The system is said to be consistent and indeterminate. You cannot determine a unique value. That's why it is indeterminate. All right. Third one, if delta is equal to 0 and at least one of delta x, delta y, and delta z not equal to 0, then there is no solution. The system is, anybody? Inconsistent. The system is said to be inconsistent. So this method of solving an equations, this method of solving equation is called the Crammers method. And you can see by this logic, we showed it for two unknowns. We solved and showed it. For three unknowns case, you can show that this is what the solution will be: delta x by delta, delta y by delta, delta z by z. The calculations will be very long. Okay. Now you can have not just x, y, z. You can have any number of unknowns and any number of equations. Meaning the number of equations should be equal to the number of unknowns. Only then you can solve. If you have two variables, you should have two equations. If you have three variable unknowns, then you should have three equations. If you have five, you should have five equations. Okay, then we and when we apply this rule and check, then we can solve. So even if we have 50 unknowns and 50 equations, you can get by evaluating determinant. And determinant evaluations are very easy nowadays by advanced computers, and there are so many softwares. You can substitute a determinant of order 100 by 100 or 1000 by 1000, and it can solve, which humanly it will be very, very difficult to solve. The computer can solve it very, very fast. So this method, we can solve the equations whenever it is required. That is why it is very, very useful. Matrices and determinants are extremely useful. Extremely. So this is the method of Crammers rule. Now there is another method of solving. We'll end here. Just a second.
So you have muted yourself, sir.
Sorry, there was an international call emergency call which I had to attend. Okay. So method 2 for solving simultaneous equation. This is very useful method, extremely useful, more than the determinants, is matrix inversion method. This is called as matrix inversion method. Okay. Now, let us write these equations. All right. Linear equations, system of linear equations. System of linear equations is a1x plus b1y plus c1z equal to d1. a2x plus b2y plus c2z equal to d2. a3x plus b3y plus c3z equal to d3. Okay. Now, because we know how matrix multiplication is defined, actually how matrix multiplication is defined is because of need of this, solving this. So we can write this in matrix form as, observe this, in matrix form we'll write this as a1 b1 c1, a2 b2 c2, a3 b3 c3 multiplied by a column matrix x y z. This will give you another column matrix. Got it? This is what? 3 by 3. This is 3 by 1. Product of 3 by 3 into 3 by 1 will be 3 by 1. See the product. A1 B1 C1 multiplied with XYZ, you will get A1X plus B1Y plus C1Z will be equal to D1. So A2X plus B2Y plus C2Z, A3X plus B3Y plus C3Z equate. So in the matrix form we can write like this. Now advantage is this. You observe this. We will call this matrix as A. This matrix is matrix A. This matrix is matrix X. And this matrix is matrix B, capital B. So we have A, matrix A times X is equal to B. I want to solve for this X, X, Y, Z, I want to solve. I will multiply with inverse. Both sides I'll multiply with inverse. A inverse A becomes I. A inverse A is I, identity matrix. Then from here we get X is A inverse B. I into X will be I. No, sorry, I into X will be X. So we get X as A inverse B. Straight away you will get solutions for X, Y, Z. Matrix methods are used primarily for this, solving this simultaneous equation, of which matrix inversion is one of the key methods. You understood? We write in the matrix form coefficients of x, y, z multiplied by a column matrix x, y, z is equal to constant.
Sir, if we are given with four equations, then what would be the solution, sir?
4 equations and 4 unknowns.
Yeah.
Same, A inverse B will be equal to X.
Um,
As long as
maybe
A inverse exists.
maybe yeah.
As long
Maybe
as
any
A,
solution.
listen. A inverse is adjoint A by det A. Correct? The determinant must not be equal to 0. If determinant is equal to 0, then you will not get solutions. A inverse will not be defined. If determinant is not equal to 0, A inverse will exist. So A inverse B will give you the solution. Did you understand?
Yes, sir. Yes, sir.
So this is called matrix inversion. So today's class, we discuss solution of simultaneous equation by 2 methods, Cramer's method and matrix inversion method. So we will do some small simple problems of 2 by 2 and maybe one problem of 3 by 3 to show how we can solve using matrix inversion. Tomorrow's class we do this. All right. Okay, we'll stop now.
Sir, I have a few doubts.
Few doubts, huh?
Yeah.
Can we do it tomorrow if you don't mind? I have a class following this in another 15 minutes, 15 to 20 minutes, and then again I have another meeting. I'm fully tight today. If you don't mind, we'll do tomorrow. On what topic?
Sir, I have it on limits.
Okay, how many questions?
Sir, it's just a concept. I have doubt in the concept. There's no question actually. Only like one question or two. That's it.
Okay, just a second. So